Let's talk about the proportion idea. A proportion is nothing but a count measured in relation to a whole. So when we calculate a proportion, we take the number in that part and we divide by the number overall. Sometimes the proportion is the number of successes divided by the number of total options, but we're not always talking about successes here. Sometimes we can be talking about failures. So let's look at a silly example before we move to our serious example, which is the real content here. What proportion of my family is bald or nearly bald? So my kids will confirm for you that I count as one, and nobody else is, so that makes the number in the part being counted as bald 1. There are 4 people in my family, so that gives me 1 in 4. So we can say that the proportion is 1 in 4. P equals 1/4. So we could also say P equals 0.25 if we wanted to convert that to decimal. Now, those are both correct answers to this question. We also often like to express proportions as percentages. In order to get a percentage out of this raw number here, we simply move the decimal 2 units to the right. So we say P equals 25%. The truth of the matter is a proportion always lies between 0 and 1. It can't be greater than 1. But when it is expressed as a percentage, then it lies between 0 and 100. So we would say P equals 25%, or 25% of the people in my family are bald or nearly so. So that example is mostly for my kids. Let's get to a serious example, and we're going to use the COVID-19 statistics to calculate a more serious case of a proportion. So what we're going to do is we're going to think about proportions in relation to the COVID-19 statistics. So it's not obvious how we should do that. We're going to need some numbers. And so let's introduce some numbers here. So before I introduce the numbers, I should say, since this is a recording, today for me is August 23rd, 2020. When you view this recording, it may be later and the numbers may be slightly different. In fact, they almost certainly will be slightly different. So here we go. We have the number of coronavirus deaths, and I'm using US data here. And at this, so today is 8/23 for me anyway, and so this number is 176,000. That's approximate. We're not going to keep lots of digits of accuracy in either the number of deaths count or the population of the US. So the population of the US at the moment, this is also a variable. It changes less quickly than this, but it's also variable, is about 328 million. Again, that's an approximation. And so we can use these two numbers. This is the part and this is the whole, and we can use these two numbers to create a proportion. And so we get 176,000 over 328 million. And this works out to about 0.00053. Let's carry one more digit of accuracy there. So that's about this number. You look at that number and you think, wow, that's a really small number. And I suppose on some absolute sense of, in some purely numerical sense, that is a very small number. But it's a tremendously significant number, even though it's a very small number. So let's express this as a percentage, because that is a point of confusion here. As a percentage, we can say 0.05%. Now, what does it mean? It's, throw a number at you. What does it really mean? That's the important thing. So 0.05% of Americans have died from COVID-19. That's what that number means. Now, I want to make sure that you're not confused about what 0.05% means. That does not mean 5%. Right? I've already moved the decimal 2 units to the right. This is not 5%. This is 0.05%, or approximately 1/20th of a percentage point. So that's not 1 in 20. That's 1/20th of 1 percentage point, which is actually 1 in 2,000 approximately. So approximately 1 in 2,000 Americans has died of COVID-19. So you can see here that this is a very small number on some sort of simplistic numerical scale, but it stands for something um, terribly, terribly huge. So now this is a proportion, right? But have we really done this correctly? Well, it depends what we're trying to accomplish, right? Um, Depending on what you're trying to learn about the situation, maybe you want one calculation, maybe you want another calculation. Um, is this a reasonable measure? Well, this is a reasonable measure of something. This is a reasonable measure of maybe how much the nation has been already tragically affected by this disease. But one thing that it's not actually a reasonable measure of is the lethality or mortality of the disease itself, because most Americans have not been exposed and have not been infected with this disease. So if we really want to, if what we're really trying to measure here is the dangerousness of this disease, then we should not measure the mortality out of the entire population of the United States, because that doesn't make sense because we haven't all been exposed. So instead, we should measure the number of deaths out of the number of cases. And so this makes a more reasonable measurement of just how dangerous the disease itself really is. So, so let's transition here and measure out of the number of cases. So when we say the proportion is the number in the part divided by the number in the whole here, what we're really seeing in this shift here is that the whole is itself not quite given in the conversation, right? The number in the part, in this case, would be deaths, but what do we count as whole? Do we count that as the whole world, the population of the United States, the number of people infected? It's not quite clear. So there's a lot of thinking to be made in what we really should be counting as the part and what we really should be counting as the whole. So let's change this and calculate in a different way. So let's take the number of coronavirus deaths and divide by the number of cases. Now, again, on August 23, we can calculate this as about 176,000 divided by, let me look it up, about 5.3 million. So I need to look it up, sorry, 5.38 million, 538,000. So that's the approximate number of US cases today. I mean, not cases today, but cases throughout the course of this pandemic. And that works out to be approximately 0.031, 0.031. And as a percentage, P equals 3.1%. And this is a mortality rate. This tells you the rate of death per case. It's pretty high, and that means that the disease is extremely dangerous. It might not match the mortality rate that you've seen in the news and that you've heard people announce. And so I owe you an explanation for that, right? This is the most simplistic way to calculate the mortality rate of a disease. You take how many people have died from the disease and you divide by how many people have had the disease. We've got 176,000 deaths, and we've got about 5.3 million confirmed cases of the disease. So why am I calling this simplistic, right? Isn't that the only way to do it? Well, yes and no. You see, these 176,000 deaths from coronavirus are confirmed deaths, and this is a count on the number of confirmed cases. But the complexity with any disease, but especially this disease, is that there are many asymptomatic carriers, many asymptomatic cases. And they are not counted. Well, actually, some asymptomatic cases may be counted among here if they're confirmed, but there are many unconfirmed asymptomatic cases of this disease. And so if we're measuring the dangerousness of this disease, the disease is not lethal for those people who carry it and have no symptoms, right, by definition. And so, but they do have the disease. I mean, they are carrying the virus. And so they should be counted in here. Now, in order to correctly measure the true level of dangerousness of this disease, we need to divide not by the number of confirmed cases, but by the number of all of the cases, at least since we're reasoning about the United States, all US cases. So this is tremendously hard to do because we have about 5 million confirmed cases, but obviously the unconfirmed cases haven't been confirmed, they haven't been measured, they haven't been identified. And so we're reasoning about what we don't know. And it's very, very hard to reason about what you don't know. But by using science carefully, we can make some educated guesses. Unfortunately, the educated guesses that we currently have access to are kind of all over the map. So one published study recently estimated that about half of all cases are confirmed. And this is kind of, so in other words, we should double this number, 2 times 5.38 million. So one recent study indicated that we are probably, in other words, we're probably detecting about half of all cases. And the true infection rate is, the true number of infections is about double what we've correctly identified. This would give us an IFR, which is half this size, which is 1.5%. This would give us a proportion of about 1.5%. But this is very, very controversial here. The idea that, you know, is it really only 2 times? In fact, other studies would say that it could be as large as 10 times. If you believe that, then we should multiply by 10 here to get the true number of the true number of infections in the U.S. population should be 10 times what we've identified. This is this pessimistic or is this optimistic? It's both, actually. It's pessimistic about how well we have detected the cases. It says that we've only detected about 10% of the cases. But it turns out to be optimistic about the dangerousness of the disease, because that's 9 out of 10 people that we haven't even detected, and the disease is presumably not very dangerous for those individuals. So this large number 10 here, we could argue about, like, we don't know. It could be 2, it could be 10, it could be somewhere in between, or these studies could at this point just be wrong. There's a lot of unknown here, and there's a lot of guesswork. And the reason it's guesswork and unknown is because we're reasoning about the unseen. We're reasoning about the cases we don't see. So this would be 0.3%, about 1/3 of 1%. So this perhaps helps you understand why the mortality rate of this disease is not well understood. You have scientists who say it's about 1%, it's about 2%, it's about 0.5%. And this has been playing out for months now, that people are sort of trying to estimate this, and there's a lot that we don't know. Fundamentally, when people die from this disease, we tend to know, I mean, not always, but we tend to know because of the symptoms. When people simply are infected with the disease, we don't always know, and it's very hard to know precisely things that you don't know. So that's why the true mortality rate of this disease is very hard. Now, I should say, I want to say a lot of things about this in summary. In the context of epidemiology, this is called the CFR, the case fatality ratio. It's a ratio of the number divided by another number. So that's the CFR. And these numbers here are called the IFR, the infection fatality ratio. The IFR is much harder to know about, and I don't really know whether it might be this number, or even something maybe not within the range of these numbers. Maybe it's 1%. I think it's a reasonable ballpark guess, but it could be somewhat outside that range. This is in the context of this science, this is called the CFR, this is called the IFR. CFR tends to be easier to estimate with some precision. Of course, we never know any of these numbers exactly, or we rarely know these numbers exactly, but we tend to be able to estimate the CFR with some precision, and 3% seems to be a good measurement of it in this case. But the IFR is quite hard to measure precisely because of what we don't know about it. It's when you're faced with this uncertainty, it's difficult to know what we should hope for. This 1.5%, if true, records a higher fatality rate, and so that seems like the bad case. But this 10 times records a higher estimate of how many people are actually infected and how out of control the pandemic really is. And so that seems more pessimistic, and it's not clear which of these things we should hope for. Of course, it's not something that we get to choose. It's just the nature of the disease, and we're just recording how much we don't know about this disease. Um, so mathematicians like numbers, and we like to understand things in terms of numbers. There's a certain comfort in the numbers, and there's a certain comfort in knowing things that we didn't know before and being able to calculate things. But um, the most important number here is not this proportion or this proportion or this proportion or this proportion. The most important number is this number. Um, and if there are lessons to be taken from this, it's, I mean, in the context of a statistics course, you should understand how we calculate a proportion. But in the context of a national tragedy, the lesson that we should take from this is that this is a record of our national failure to deal with this vicious virus. And this is the most important number on the chalkboard. So hopefully this has been useful and helps you understand proportions. Hopefully it gives you a little bit of context for why people are working so hard and generating controversy about how we measure this disease. One more notice before I let you go, and that is that these are three different computations. They are all very, very simplistic. They belong in an intro stats course. These are not the computations that real epidemiologists are doing. Real epidemiologists are doing things far, far more sophisticated than what you see here. So if you see Dr. Fauci reporting on a number, I don't want you to think that he's done nothing more than I've done, right? The real scientists are working hard with very, very sophisticated models. And these are three, simplistic computations that help you understand in an intro stats course, but it is certainly not, I don't want to represent that this is how far science has gone here. Epidemiology is far, far more sophisticated than what I'm giving it credit for, and I want you to understand that so that you don't underestimate the kind of expertise that we really have in this field.